machine learning basics class with Python. And we would be doing a little recap on last classes concepts, and then we continue from there. So today we want to wrap up with regression problems so that we can go into classification problems from next class, right? So let me just go back to the notebook that we used for last class. So last class, we were trying to do a prediction of USA house prices, and we worked on this notebook. So just a little recap, we have in machine learning, we have different type of problems. We have the supervised learning, the unsupervised learning, and the reinforcement learning. Under the supervised learning, we have the regression and classification. And for regression problems has to do with you predicting a target that has a continuous form. For example, like prices, humidity, temperature, anything that has a continuous variable, a continuous target. So that's when you have cases like that, you're dealing with regression problems. However, for classification problems, it has to do with categorical labels, where your labels, what you're trying to predict is a categorical label format, such, for example, when you have high, low, medium, or something that has to be categories. Okay. Today we'll just be wrapping up with this notebook. So last class we're going through this notebook using Python. And then we're trying to explore the data. We did the data exploration and we got to the end where we're making predictions, right? And when we're making our predictions, we're trying to use our test data sets. So we're going to go through another example, and so that we would further strengthen our understanding on building machine learning models using regression. Okay, so I just want to wrap up with this because I think we're not fully we didn't fully conclude this part before going to the next thing we have for today. So after you've finished building your model, we have different steps, like I highlighted earlier. When you're doing a machine learning project, you have the data gathering, which we have done. This data has been provided for us, after which you have to explore the data, checking the information in the data, checking the different number of rows, number of columns, and then you do some data visualization, exploring the data. You do some exploratory data analysis, right? Checking different features, the relationship between the features and the label, and all of that. And then moving forward, after doing your exploratory data analysis, you go further to start your model development. But before you train your model, you have to split your data into you have to first of all select the features that you want to use and the target. Here, we're selecting all other columns rather, apart from the price and address. And here, price is our target, price is our Y, and X is the other features we have. And then after selecting your feature and targets, then you split them into the training sets and the test sets, which we did here. I'm just doing a quick recap. After the splitting, then you import your machine learning model here. In this case, it's a linear regression model here. You fit your model. This is a place of training the model. After training the model, then you evaluate your model. So when you train your model, after training your model, your model would have some parameters. Remember, our formula for linear regression is y equals mx plus c, or either way, mx plus b or mx plus c, where your y is your prediction. That's what you're trying to predict, and then your x are the features in your data set, and your M is the coefficient the coefficient of each of those features, and your C is your intercept, or your B is your intercept. So here you can see that you can print the intercepts from that model that we built that's using your lm.intercept, and then you can also print the coefficients for each of those features. And when you put them into a data frame, you can see that you have all of this, in a tabular format. And then you can explain your model by saying that even when you hold all other, now this is it's a linear model, right? Where if you're to write out the formula for this this particular model that was built, you have something like your Y. I won't be able to load it because I've not loaded it from the first one, but I'll just write it out. Your Y in this case is your price. Price equals every of the coefficient, like 21. Let me change it to a markdown. You have 21 point, I can just round off 21, 20. Let me just say 20, 22. 22 of the average area income. Average area income plus we have the 160, 166, 102, 103 of the average house. Let me just use the house age. I'll just use something like average house age. Then plus 119,895 of the average area of bedroom, average number of rooms, and then plus 11901 average number of bedrooms plus 15 of the average population, plus now our coefficient is a negative value. These are coefficients. I mean, our intercepts. Our intercepts is equals it's supposed to be a plus, but I mean the formula is the formula for this is, right, Y equals mx plus c, where your m can be m1, it can be m1x1 plus m2x2 plus mx or mn. Let me use mi xi, where I and x, I mean I is maybe the last value, right, plus c. So this is the formula for this particular linear regression model for the linear regression algorithm. But then applying it to this case study, you have something like this. Our coefficient is -26. Then we have this. So here now you see that your model has built a new, using linear regression, it has built a new model such that for future prediction, if you give it the average area income value, the average house age income value, the average number of rooms, bedrooms, and population income value, it automatically calculates the price of that particular data points in future. So this is the formula that will be used to build future model. So, but then that's the way to interpret what you've done using linear regression. This is peculiar to linear regression because it's formula for linear regression. So it's just interpreting the coefficient, holding all other features fixed. A unit increase in the average area income is associated with $22, an increase in $22. So now for you to interpret this particular formula, you can say that a unit increase in the average area income is associated with $22 of price, and as well for other coefficients. Okay, so moving forward, it's not enough to just generate the formula. You have to evaluate to see if this formula is actually working well or not, or if it's actually going to give you a correct value or not. And how can you find out if it will give a correct value or not? Is by comparing it with the test sets that you have actually you've divided, comparing with the test sets that have been held back. So what you're going to do next is to make predictions from your model that you built. So the model we built is called LM. That's the name of the model. LM has a method called predicts. So you can apply this LM.predict on the test sets. We divided our data set into the training sets, the X train, X test, Y train, Y test. We used X train and Y train to train our model. So to make prediction, you're going to use your X test and Y test. X tests will be used to generate your predicted test. And then you're going to compare your predicted Y tests, your Y predictions with the original test value. I believe you understand what I'm trying to explain. So let me just continue. I don't want to dwell so much on this example so that we can go through other examples and you further understand the concept. So why I'm spending more time on this model is that once you understand the concept of building a machine learning model with, even if it's one algorithm, it applies to every other algorithm. So it's just for you to know how to interpret your model. How to interpret the results of each of those algorithms. But the building, development, everything is the same thing. It's the same approach. So that's why I'm taking time to explain this to you. All right. So after you have created your model, you've made your predictions, you have generated the formula, what you need to do next is to make your prediction, and then you predict with your X tests that had been held back, and then it has generated new predictions. So we have the predicted Y and the original Y, which is our Y test. So to calculate the error, we have to compare the difference between the predicted Y value and the original Y value. And doing that, we have different metrics that we can use. Okay, so we have the root mean squared error, the mean squared error, R squared, mean absolute error. So, but in this case, we are using the root mean squared error. And how do you use it? We have to import the mean squared error. We imported it at the beginning of our model from sklearn.metrics, import mean squared error. And after you do your import, you'd have imported that, and then you can now say mp.square root, that is, you're taking the square root of the mean squared error, then you're giving it the test set that you kept and the predicted Y that your model predicted. So when we compare it, we see that we have a very large error value. It is very large. And so what do you do? We've built a model that can make predictions, right? But now the next thing is to start optimizing and improving our model. How can we reduce the error? What are the things we can do to reduce the error of this model? And that brings us to model level. There are a lot of processes. There are so many things to consider in optimizing the performance of your model. Right, so building your model is one thing, but then there are a lot of statistical functions. There are a lot of statistics involved, so that what you're producing at the end of the day is something that it's acceptable, at least if at a confidence level, you can say that, oh, your model is doing very well. And that brings us to evaluating model performance. But then we won't touch so much on that in this during this boot camp. I'll just mention some basic things that you need to know, because that's another, area entirely, because there are so many things, papers involved, so many, research that has been done in that area. But I'll be mentioning some things that you need to take note of when you want to optimize the performance of your model. Okay, so let us quickly move from here. Okay, now for example, okay, what I was trying to show you last class, I was trying to show you that you can, if for future values, maybe you want to make prediction of a singular value in future. I was giving you an example. You want to make prediction. I think it was around here that I was getting an error. Was it here? Okay, I think it's around here. Yes, this place. That when you want to predict, you want to make, for example, you have a new input from a user. Maybe somebody in future wants to know the prices of house around the area, that particular area, and then the person supplies the average, all the parameters that we have here in our features: the average income, average house age, number of rooms, number of bedrooms, and area population. The person supplies his average income at $67, the average house average house age, the average number of rooms for, and all of this. So you can actually use your LM.predict to make that prediction. And when you load this, it's going to give you the price of the house. All right. So that's the beauty of predictions, using your machine learning model. But it's not just to make prediction. You have to be sure of what you're using to make prediction, because ML is very, very sensitive. And then you can't just, most especially when you're working with data set like health related data sets, when you're building a model to predict whether somebody would have cancer or not. That's very, very sensitive. Or maybe something that has to do with fraud, or something that has to do with, there are so many things that are really, really sensitive in life that you can't just afford to build anyhow model. You have to be very, very careful when you're building your model. You can't just push any model out to production because of the sensitiveness. One can be sued for building wrong models. So you have to there are a lot of things that has to be factored in when you're making predictions. So it's not just making predictions. You have to put a lot of steps into place to build effective models. All right. So that was just a run through of, a recap of what we did last class. So today I'll be showing you, we'll be doing more examples. I'll be showing you some ways to optimize the performance of your model for regression. And we'll still be using linear regression. There are other regression algorithms. Let's proceed so that we can quickly cover some things today. I want to make sure I touch on the key parts of regression today, so that next class we can move to classification algorithms. Okay. For this notebook has been updated on the LMS. You can see it's under I think under Monday. And it's also on the table where we have the recordings. So I would also update the notebook for next class as well. Okay, so I want to quickly touch on the evaluation metrics, the differences in mean squared error, mean absolute error, and root mean squared error. It's going to help you, it's going to help you. I'm going to just use a very simple case so that you'll be able to understand what the difference is. So after this, we'll do a short quiz that we're supposed to do in the last class before we move into the new data set that we'll be working on today. Okay, so for regression problems, we have different ways to evaluate our results. We can use the mean absolute error, the root mean squared error, or the root mean squared error, the mean absolute error, or the mean squared error. So the mean squared error, they are all evaluation metrics for evaluating continuous variables. But I'm going to start with the mean absolute error. So the mean absolute error is just the absolute mean of the absolute values of errors in your data set. Now, for example, we have a data set like this, where we have our true values as 100, 50, 30, and 20. And then we have our predicted value as 90, 60, 50, 30. So what this means is that this were the original values for maybe for the house prices, right? That were held back. And these were the values that the model predicted. So how do you use your mean absolute error to evaluate this? So originally without using any Python function, right? You can calculate your mean absolute error using your mathematical formula. It's just the subtraction. When you take, how do you calculate your error? Your error is what? The true value minus the predicted value. So you can say that, to carry out subtraction, you have to use a list. I mean, an array. You can't use list to carry out a subtraction. So with an array, you can easily do your calculation. But for the sake of explicitity, I want to show you how it really looks like in practice. So I'm going to create another. Let me just say something like error. I can say error is equal to 100. I'm going to calculate it manually, right? This can actually be calculated using your array, with just your formula. But let me just use this. So your mean absolute error, normally without calculation, would have been 100 minus 90 plus 50 minus 60. I'm using brackets so as to control the ordering of this. Then we have 30 minus 50. And then we have 20 minus 30. Okay. So after taking your mean absolute error says, take the error, these are the errors, right? The true value minus the predicted value. Then take the absolute value of this error. And how do you take absolute value using Python? You can use your ABS function, absolute value, ABS. Let me just put ABS in front. ABS. Okay. And then when you take, when you do 100 minus 90, it gives you a positive value. The absolute value, what absolute value does is that it converts every negative to positive, and positive remains the same. Okay, so this will still be positive 10. This will be this will be minus 10, which will become positive 10. And then it does all of that. And then because you want to do your mean absolute error, right? Your mean absolute error would now be the mean. How do you calculate the mean? Mean is the sum of all the values in a particular list divided by the number of the values, right? That's the way to calculate our mean. Maybe you have 5 elements, 1, 2, 3, 4, 5. What's the mean of those 5 numbers? Is 1 plus 2 plus 3 plus 4 plus 5 divided by the 5 numbers. So this here, in this case, this would be this plus this plus this plus this divided by 4. That would be our mean absolute error. Okay, so we'll have what? So let me print out the value. Let me just print out mean absolute error is Okay, so you see that it's 12.5, right? So that is just the simple way to calculate your mean absolute error. And if you want to calculate your root mean squared error, your root mean squared error is just saying take the square roots of the, sorry, okay, this is mean absolute error. Now I'll explain the mean squared error. But if you want to use your Python formula to calculate, instead of doing all this manual calculation, there is this metrics function inside sklearn. You can import it from sklearn. From sklearn, import metrics, and then you can always say metrics dot mean absolute error. Instead of calculating it manually, you could just say metrics. Let me just copy this so that I don't have to type. You could just say your metrics dot, how do you access a function inside what we've learned before? You can just say metrics dot mean absolute error. Then you supply it the true value and the predicted value. And this automatically calculates your mean absolute error. So I'm going to do this mean absolute error 2. So this is going to just print out your mean absolute error. So I can say error 2 equals metrics dot mean absolute. Here I can just remove all of the sample error. And so you see here now that it's the same thing. Whether you're doing it manually or you're calculating it using Python, it's the same thing. So that's just the idea of your mean absolute error. So I'll run quickly the mean squared error. The mean squared error is the mean of the squares of error in your data set. Now, in the absolute error, we took the absolute value of our errors. But the mean squared error, you are taking the square, instead of the absolute value here, you are taking the squares. You can see it 100 minus 90 raised to power 2, the other one raised to power 2, and this raised to power 2 divided by 4. You're taking the mean of the square of your error. So is that explicit? All right. So when you do your calculation manually, you get 175.0. And if you're using Python, metrics just mean squared error. You supply the true values in a list, then the predicted value, and then you see that it's the same answer. Now, the root mean squared error is just the square root of the mean squared error. So after doing all of this, take the square roots. That is what your root mean squared error is. So when you go here, go to the next one, you can see that if we're calculating it manually, this is our mean squared error. You can just take the square roots using np the square roots of the mean squared error, and this gives you the root mean squared error. And then you can use your Python formula to do. Python doesn't have an inbuilt formula for your root mean squared error. So you can just do np the square root of metrics dot mean squared error, and it gives you your root mean squared error. So from my personal research, I noticed that root mean squared error is most frequently used because it's more easy to interpret. Most times, people understand mean absolute error as the mean of the absolute error. So it's easy for people to understand. But then MSC is more popular because it punishes larger errors. Here, if you notice that here is your absolute value is making your minus 10 and 10 to be the same thing, of which is not supposed to be. Minus 10 and 10, they are different values. So your absolute value is equating these two errors as the same, and which can have an effect on your final error value. So that's why most persons say, okay, mean squared error is better because you're taking the square root. When you're taking the square root, it removes the negative value 2, and then it's also making it the same thing as well. Is increasing the number, because when you take the square of minus 10, it gives you 100. When you take the square of 10, it gives you 100. But then it said that it punishes larger errors by squaring it in a mathematical function. But the square roots tends to reduce the error number, because you see your mean squared error, because of the square because you squared the error, you're having a larger error. than taking the square. When you take the square root, see the square root reduces the error. All right, so that's just difference between, that's just a difference, simple small difference between the mean squared error, mean absolute error, and the root mean squared error. So at this time, let me see if I've been able to open. I was trying to open up the Slido application. Okay, it's faster today, so that I can we can quickly do a short quiz that we didn't do last class, and then we would get into another data set. Okay. All right. I'll share the link. I don't know, do we have any questions? If there are questions, we can drop it in the chat. If there are no questions, this is just a very short, very short quiz and simple. Okay, so I expect everybody to be very fast about it, and it's a piece of cake with all the explanations. So I'm going to share this link with you all on the chat. So you can just access the chat and join it. Expecting you all to join. Okay. Let's all try to attempt this quiz. It's very easy. So we have 3 persons that have joined. Please, I want more persons to join. The link is on the chat. You can just click on it. It will take you to the Slido dashboard. At least I want half of the at least 80% of the class to join before I start the quiz. Can we all see the link, or do you need me to share it again? Still waiting for you all. Like, I'm giving 30 more seconds. We just have 3 persons join. Please, let's join. Let's try the quiz. It's very easy. It's not difficult. Okay, because of our time, we'll start the quiz. Let me start the quiz so that we can we're starting now. You can still join if you can. Yeah. So the first question says, regression involves predicting a known label that is a dash variable, continuous, categorical, sequential. Regression involves predicting a known label that is a dash variable, continuous, categorical, sequential. Okay, so the answer is continuous. We said that if you're doing a regression problem, right, you're predicting a known label that is continuous. Is a classification problem that you're predicting a known label that is categorical. So thank you all for attempting that. Let's move to the next one. Which of these is not a regression problem? Predicting salary, determining glucose level, predicting whether a patient is diabetic or not, predicting student's grade. So which of them is not a regression problem? There's one that is not a regression problem. And we all got the answer. Thank you all for attempting that. We have predicting salary from years of experience is a continuous variable, right? Then predicting glucose level from age of patients, you're predicting a continuous function, which is a glucose level, Predicting whether a patient is diabetic or not, it's a classification problem because you're predicting a classification variable, whether you're saying whether somebody's diabetic or not, yes or no. When you're predicting yes or no, true or false, high, low, medium, and all of that, that's a classification problem. Predicting students' grade based on study time. So grade is a continuous variable as well. Grade can be treated as categorical, but most times it's treated as a regression problem because you might have wide range of grades. And the more you have a wide range of value, just treat it as a regression problem. All right, thank you all so much for that. That was just a short quiz. Thank you everybody that attempted the quiz. I'm sure you learned something from it. Okay, now let's go to Boston dataset analysis. So we have another regression problem that would like to, attempt. I'll show you how to go through the process, just like we did with the USA house prices. So the more you try out different problems, the better you become at building machine learning models, building different kind of machine learning models, and because no problem is actually the same. Oh, you can have similar problems with similar challenges, but then you find out that there's always something new to learn, and that's why it's good to try as much as possible to keep attempting, keep trying. Even if you're getting very low accuracy, keep trying to improve them, and then you see that you're good. You get better and better. All right, so this data set was gotten from, I think it was gotten from Cargo, or I forgot to drop the link, but this is the reference of this data set. It's a very popular data set, Boston. Okay, so there are some features in the data set. It has about 506 rows and 14 columns. And then data set contains different features. Most of those features, they were used, the naming convention was just like an acronym. So there's this description. So usually, sometimes when you get your data set, you could have a data description of your data set. Sometimes some people call it a data dictionary, where you have more specific explanation of different features in your data set. All right, so we have in this data set, we have the per capita crime rate of the town represented in cream. We have the proportion of residential land zoned for lofts over 25,000 square feet, proportion of non-retail business acres per town, Charles River dummy variable, it's equals to 1 if tract bound river, or 0 if otherwise. So this is another feature in the data sets that has to do with the river. All right, nitrogen oxide concentration, average number of rooms per dwelling, and all of these, the age of proportion of owners occupied units built prior to 1940. So the most important feature that we are interested in is the median value of owner occupied homes in 1,000 US dollars. So we want to find out, we are faced with a challenge where we have existing data sets of all of this, with all of these features, that has the median value of people that have occupied a particular house with a particular amount of dollar range, that is the prices of those houses, the median value of the prices of those houses are listed in this data set. Now, can we predict what would be in future? Maybe we want to find out the median value of the prices of houses in that a particular area. How can we build a machine learning model to solve that problem? Okay, so this is another data set that has to do with prices of houses, median value of prices of houses. And this, when you talk about price, it's a regression problem. So before we get into this, there is this exercise that we'll be trying on our own. Okay. Okay, it's an e-commerce, so it's something different. I was thinking, should I use the Boston or should I use the e-commerce? But I wanted you to just try this e-commerce yourself, so that you would have like an experience of it's very, the notebook has been designed in a way whereby it would easily give you a guideline on how to build your machine learning model. So you just do your imports, you get the data, right? So the answers are there too. You get your data, it's giving you instructions on what to do. Check the head and the steps to take, do exploratory data analysis, we create some plots, we create the pair plots, do some implots, do your training, your test, predict the test data, do a scatter plot of the test and predicted value, evaluate your model, calculate the mean squared error, and all of that, which we have all talked about in class. Then you calculate, you can also plot your residual histogram to show how the distribution of your data. So we'll talk about that as well, using your plot.hist on your your house prices, that is the predicted value, and then you interpret the coefficients of your results. What do you think? Which of the coefficients do you think the company should focus on more when they have to build a mobile app for their website? So this data set has to do with an e-commerce data set, where you have the email address, the avatar, the average length, time on app, and all of that. If you check further, you see all of the data set. So here, what you're going to be predicting, you'll be predicting the yearly amount spent, time spent on the application. So that's what you're trying to predict. Okay, so I just thought to mention that. And let me go back to what we have for today, the Boston data set. Okay, so on this data set, I just explained the different parameters. So the first thing like we do is do our imports, import pandas, numpy, matplotlib, seaborn, because you might have to do some visualization. Can you all hear me, please? All right, great. Okay. Okay, so after importing the libraries, you read in your data sets, and then you have these features in your data set. And here you identified that you want to predict the median value of the houses. So here you can see the first 5 records, but then we need to go into the first step, which is data preparation and preprocessing. So you can check the information regarding the data sets using the .info method, the name of the data set, which is Boston, and then when you're checking your info, you notice that you have 506 rows. So usually, sometimes you might even have about 1 million rows, and that's why most times in practice, you see a lot of machine learning tasks being done on GPUs on the cloud, except if you are using a very, very strong device, right? If you are using a very, very strong device that has GPU, all right? So, but then most times you see that you have to use some of these cloud platforms like Google, um, Azure, or AWS to run your computes. Okay, so but for now, these are very, very small, records which we can still work with on our personal systems. But for maybe in practice, if when you are loading maybe you could be loading data sets that are very large from databases. So you have to do that uh on the cloud. All right, so I just thought to mention that. Okay, but for now we're not focusing on that for now, so that's another, setting it up and everything, if depending on the cloud system that you're using. Okay, so we have 506 entries. We have about 12 columns. And then what you're interested in number one, you're interested in the number of null values. You want to see the quality of the data, and then you want to see the data type as well. Because if you have data types like in this e-commerce data set that we're working on, we're just giving you you're just going to build a simple baseline model, but you can take it further. If you want to increase your performance, you can try to convert this avatar into numbers, which we'll look at that in other when we are doing our classification algorithms, how to preprocess our data, how to do our data preprocessing, our one-hot encoding, factorization method, and all of that. We'll do that during the classification class, but let's just stick to the basics at this level, so that as we are going further, we can go into more advanced concepts. All right, so back to Boston. We have this. Okay, back to Boston. I'm trying to click on the interface. Okay, so we are here, and we've checked our information. It looks good. We don't have any null value, so we are good. And then we don't have any alphanumeric value or string value, so we are also good at that. So now another thing to do is you can check the description of your data set. Since there are no null values and all, you can also check the duplicate, if there are duplicate values in your data set when you're doing your exploratory data analysis. You can check duplicate values. I mean, under data preparation, you can check if you have any duplicate values, because there was one data set we're working on during Panda's capstone project class, and then we discovered that almost 80% of the data sets were the same. So if you have such in your data set, you need to treat that. You need to be sure of the quality of the data set. So you can just use your duplicated to check the number of duplicated. When you just do without the sum, this is what comes up. So you have this. It brings out any duplicate value. Duplicate column is going to bring it out. But then here, just taking the sum tells you the number of duplicate value in your data set, and it's telling you that you don't have any duplicate value. You can also check your null values, but we have already seen that, right? We've seen that here, that there are no null values. But to be sure, we can use your null function.sum. It tells you the number of null values in each of the columns, which we are sure that, okay, there are no null values. So the next thing is to go to check for outliers, out of range values in our data set. So you can do your .describe to check if they are out of range values. So what you mean by out of range values is that there are sometimes that your data sets might be, I'll touch on that a little bit during this session on skewness. I'll touch on a little bit of statistics because that's very, very important in evaluating the performance of our model, or improving the performance of our model, I mean. All right. So when you do your describe, it gives you a descriptive statistics of each of the features in your data set. So here you can see that the cream has about 506 number of records, and then the mean value is 3.6. Okay, you are interested in the maximum and the minimum, and then the average value. So the maximum value is 88. The minimum value is 0. You can see that this particular column is highly skewed. And then the median value is what? Is 0.25. That's the 50% percentile. The 25% of the data set is 0. 50% 0.2. 75% 0. So the data set is actually skewed to the left. That is skewed towards the origin of 0. How come we have a maximum value of 88? That's really, really wide. And then our average value is even 3. So that means there's something about this particular column that needs to be checked. So you can just start taking note of those observations at this point. You might not act on it now because you just want to build a baseline model first. You don't want to go ahead to start doing so many improving model performance. I mean, improving the quality of your data sets now. And then at the end of the day, after doing all those work, when you build your model, then your model is giving you something very, absurd. So you just go ahead to use do a minimal data preparation, just tidy up the data preparation to a minimum extent, and then build your first model with the data set as it is before you start optimizing the performance of your model. But just take note now of these observations that this cream is having a very skewed. So I'm going to be telling you the importance of skewness in your in the features, in the numeric features, most especially the target variable in the numeric features of your data set. Okay, so we have that. Take note of that. The cream column. Then if you check what is cream, the cream is the per capita crime rate by town. So it's even a crime rate, per capita crime rate by town. Okay, it's possible for us to have a very high crime rate, but then that's really, really out of range. So if you want to further investigate, you can just check that you want to see that the data set with the highest for just to something like Boston. Okay, or maybe the numbers that are greater than 3.6. The 25%. Okay, let me use this. So we have, but I'm just interested in the cream. Okay, so we have about 127 rows. Okay, out of 500 that is greater. So let me just increase it. It's greater than 5. Or let me use 10. So we have about how many of them? They are very, very minimal. So these are now this is the one with the largest crime rates. We have 88.897 is larger than the other ranges. I don't know if there are any. Okay, we have something of 67. So it's possible we have a number like that. So, but this is just the way to, further investigate your data set to be sure that it's not an outlier. But let's just continue so that we don't focus on that, right? And so that we can, go and do all that. But that's just an example. So you do the same thing for other ones. Like here, you can see the maximum value is 100, minimum value is 0, the median value is 0. That is very, very skewed. So the data set is showing that it's very skewed. And then this one, 75% of the data set is 12.5. The mean is 11.3. The standard deviation from the mean is 23.3. So you have a very big outlier here as well. If you check this as well, this is just okay because the maximum is 27, the minimum is still 0, and then the median is around 9, which is slightly okay. Then if you check for this is okay. This is 1, maximum is 1, minimum is 0. You can just, check through all of the record. But then what the most important feature here is our target value, right? You have to know, even if you're checking the distribution of all the data sets all the features in your data set, you have to check the distribution of the data set the targets in your data set. So I'm going to touch on that quickly. So when you're building regression model, you have to be careful about your target variable because your target variable is a continuous variable, and then the distribution and the characteristics is very, very key because it impacts the performance of your model. So if your if the distribution is not normal, I'll be explaining the difference between your normal distribution. We have normal distribution, we have the right skewed and the left skewed distribution. I'll explain what that means soon. But then you have to be sure that you have a kind of a normal distribution on your target variable to address issues like non-linearity and skewed distribution. So in statistics, skewness helps us to understand the distribution of our data set. I'm going to show you, like, I don't know if you've seen something like this before, where you have a bell-shaped, graph on how it tells you whether your data set is right skewed or left skewed or normal. And this helps you to understand it. It's crucial in decision making, most especially when you're doing risk assessment and you want to predict future trends in your data set. So when when you do a dist plot, this is a dist plot on our target variable. As you can see here that our data set, the graph is right skewed. That is, the mean value is less than the median and is greater than the median and the mode. So when you have a right skew, which is also called a positive skewedness, your mean value is around here. Your median value is around here, and then your modal value is around here. Let me check for an image on skewness so that I'll show you what it looks like. Okay, let me see if the one that would really, really show you. Okay, I think this one would do. So I don't know if you can see this image. Let me spotlight it. Oh, sorry. This is taking a screenshot. I don't want to take a screenshot. I just wanted to, if I double click on it, it's going to take me to the website. I don't want to go to the website. I want to just All right, but I don't know if you can see this image. You can see here that this is a negatively skewed. You can see the tail end is towards the origin. The mean is less than the median and the mode. Here you have a symmetric, a normal or uniform distribution where the mean is equals to median and equals to the mode. And then here you have like what we have there is a positively skewed distribution where the mean is greater than the median and the mode. So here you see. Okay, all right. So let me just start from correlation then. Okay, so about correlation, I was explaining that there are ways by which you can evaluate you can know the kind of features that you feed your model with. So you have to understand, you have to find the correlation between your different features and then the target variable. Here in this case, we have the median value. So on this table, you can't actually know you can't see it at a glance. You can't see your correlation because the features are kind of many. So what you can do is to use an heat map to display it. So when you do a visualization with your heat map, and you can just pay attention to the lower part of the heat map where you have your targets and then you have the other features. Okay, so after when you get to that point, you can start checking that, okay, for different figures, which one is the highest correlation between my target and the other features. And here you can see is the room that is the highest correlation. And I was trying to explain earlier that correlation, there are different ways for improving model performance. I mean, selecting your features. That when we get to, I'm going to try to touch on that. I don't know because we've spent some time. You could not hear me, so I'll try as much as possible to touch on that as well. So we have several ways of selecting the best features. So I want us to run through this, rebuilding the model first, then before we now go into feature selection. So correlation metrics is one of the ways by which you can select your best features. And I was explaining also that correlation is not causation. Correlation, that if a feature is highly correlated with the target, doesn't mean that that feature was the one that, is the one that would likely cause the performance of that target. And I was giving an example. For example, we could look at rainfall, and or let me use temperature, for example, and you have different features like the total number of population, the income of people in that area. I don't really know so much parameters of regarding weather, but maybe we have something like humidity, we have something like whether it rained in previous days or not. So if you have all of those features, and then there's one feature, for example, population, that is very, very strongly correlated with your targets, that feature is strongly correlated with your target, it doesn't mean that that's the feature that is going to cause the prediction of that target. So it's not necessarily mean causation, but it might be a pointer to the fact that it would rain or it would not rain. Okay, or maybe there'll be an increase in temperature, or the figure or the parameter for that particular value. So you should just take note of that a feature is highly correlated with your target doesn't mean it causes the target, but it's just a very strong feature that might be one of those things that would impact your target. All right, so moving forward quickly, we have the pair plots. Instead of doing the whole pair plot on all of the features at once, you can just take it gradually by picking different declaring you have your data, that is the Boston data. Then you declare your X variables, that is the variables you want to be on the X axis. We have the cream, the zine, the indoors, chas, and nox. And then you have the Y variables, the variable that you want to be on the Y. So I wanted 5 plots on the same line. So you can define it this way. I define your size, the aspect, and the kind of plot you want on your pair plot. It could be other plot, it could be a box plot, it could be another plot. So here I want a regression plot. So, and here you can see that when you plot this graph, all of these data sets they are not very, very well defined because of the skewness of those features. You see that most of them should start from the origin, but then they are either they are like they should be towards the origin or on I mean they should either be strongly negative or strongly positive. But because they are not normally distributed, find out that all of these features are like this. So we can just take note of that as well, that when you are improving the performance of your model, maybe you might have to take a decision of normalizing the features. Okay, but at this point, you might not have to do that because you just want to build a baseline model. So you can also do for other features, the room, the age. Now you see the one that was highly correlated, you can see that it's showing some sense of good prediction. Like we have a line of best fits on this feature. Okay, so you also can see these other features too. So moving forward, this is also another very good feature, but this is a negative correlation. All right, so this using this plot, it's going to help you to identify some very good features that might be one of those when you want to do your feature selection. And the essence of feature selection is that you want to reduce the noise in your data. Sometimes in your model, if you have 100 features, how do you streamline the number of features to maybe a very good number? You're focusing on the best features and not just all of the features that might not even add value to your model. Okay, so here you can see when we plot the we're just using another plot. All these are just visualizations just to help you identify your the good features in your model. Now let's get to training our model. The first step, like we usually do, is to select our test sets. These are all our test sets, and then the training set. Select our features. These are the features. Out of all the features, we have just one target, which is the column that I want to predict, in this case, which is the median value. So we are selecting all other columns or features, and then as your X, and then your target is your what? Your Y. The next step is to do your train test splits. That is, you have to split your data into your training set and your test set. And when you're splitting it into 4, whereby you have your X, usually you're going to use your X train and your Y train to train your model, because you want it to learn. That's the idea of machine learning. You want to use a mathematical model. In the mathematical model now can be your linear regression, it could be your XGBoost, it could be your decision tree regressor, it could be your support vector machines, it could be your lasso ridge. All of these models, they could be any model that you want to use to train your data set. So you have to split your data into your training and your test sets using, there is this library called the sklearn.model selection. So from that library, you can import your train test split. There's another library called the cross validation. So we're not going to use cross validation in this class because I just want us to stick with, the basics, so that I don't bring in so many other things that might confuse some persons. Okay, so cross validation is another way of, dividing. You can read up, you can check up on cross validation, another way of splitting your data set in folds, not just, directly like train test split. So usually when you're doing machine learning, there are a lot of things going on in machine learning. So, but there is a process. So you just follow this first, just the direct process. Then you start doing several iterations to improve your model. So, there are so many things we've taken note of before we got to this point. We've taken note of some of the features that have high variance. That is, they have They are not the symmetrical distribution of the data sets are not normal. And then you have you've taken note of the fact that there are some features that you might want to focus on when you want to build your model. Maybe you might not have to use all of your features. When you are doing your performance, improving your model performance, those are things you go back to when you are doing your model performance. Okay, but let's just go ahead to build our first model. So we are going to split this data set using our training test splits, and you are defining that you have your X train, your X test, Y train, Y test. So this is always the same thing. The only thing you're changing here is you can define your test size. Sometimes some people might decide to use here I'm using 70% of my data set and 30% as my test size. So I'm saying 0.3 is my test size. The whole size of my data is usually 1. So I'm saying 0.7 is my train size and 0.3 is my test size. So I can decide to say 0.2 as my test size. I can say 0.22, 0.18, or any figure I want to use. Is up to you. And also you can decide to set your random state as any figure too. Is also up to you to set your random state as any figure. But all of that thing is still X train, X test. They are variables that can be changed, but then it's still the same process. All right. So here now you've seen that you've selected your training test. So I'm going to be loading some of this. I don't know if I start loading it from the beginning, but I think I need to load it so that for the sake of explanation. Okay. I hope it doesn't take so long to get here. All right, so here X is not defined. I thought I loaded X somewhere. I didn't load this. I skipped this. Joint. Okay, there's a mistake here. Let me just comment this out. Okay, so here you can see that by the time you print the shape of your train set, you see that before we had 500 and what? 506. Now you see that your train set has 356 rows and 13 columns. Your your test set has 152 rows and 13 columns. So this train set, this train, X train and your Y train, that's what you're going to be using for your prediction. And your your X train and Y train, that's what you're going to be using to build your model. And then your X test and Y test, that's what you use for your prediction. So here, after your train test splits, you want to create and train your model. So because I'm using the linear regression model, I'm going to do from sklearn.linear regression. So at this point, if you're going to be using another model, right, this is where you're going to introduce the model that you want to use. This is the place where you're going to introduce the model. So it's still the same process. All right. So the process is import your model. After you've import the model, instantiate it by giving it a variable name. This is the variable name that will be the model that will be used, for prediction and all of that. So linear regression, that is, you're copying all of the linear regression function into this variable, linreg. All right. The linreg can be anything. Yours can be LR, yours can be LG, yours can be anything. All right. So, but then this linear regression is the function that you're importing. All right. So after instantiating the linear regression model, you need to fit the model. So there are some, when we get to model performance, model improving your model performance, there's some parameters that you can tune inside this linear regression model. There are some parameters you can tune here. Okay, let me just when I do my tab, sorry. It should bring out something. Okay, it's not bringing it out. Let me load it first. All right, okay, so there are some parameters that you can change if you don't want, if it like fit intercept, true, normalize, if you want to normalize maybe anything, you want to normalize your data sets, you want to copy, all of this, the parameters are being explained here. All right, that's when you get maybe a hyperparameter tuning. You can, start tuning any of these parameters. But here we are building a baseline model. So the next step is to fit your model. We have the linreg.fit. Now, the training sets that we've defined earlier, the X train and the Y train. This is where you're building your linear regression model. Okay. And then after building the model, it has learned all the patterns and everything. So when you're saying I'm training my model, this is just that line. That's everything is inside this place on that fit. So if you have a very large data set, right, and you're not using a GPU, I've trained a model for that. It took me like almost 10 hours to train because even okay, I think it was even with GPU because it was a very, very large model, right? So this thing can take you hours like to train, to actually produce an output to train. So it's that's it depends on the complexity of the model, it depends on the size of your data. And that's why you have to put in a lot of effort into selecting the best features, because you don't want to spend, and sometimes you spend a lot of money on GPUs. Like if you have to buy a GPU that would I think I heard, was it Chat GPT or something that they trained for? I can't really remember, but they trained it for several months. Was it several months, almost, or years? It took them years to train all of those models. So it's very, very expensive in terms of computing, because you have to pay either Nvidia or some of these GPU service providers money to use their GPU, because you don't have that on your own, server. So building machine learning algorithms, deep learning algorithms can be very expensive at times. So when you're training, this is just what you're training, right? And so that when you're building your model, you can't just keep training different models. You have to train, you train with a little of your data, train with, and when you're sure of the algorithm, the final algorithm they are going to use to build your data, then you now use it to do all your train. Sometimes you do batch processing, you train in batches, you train, retrain, and all of that. All right, so this is the place of training. After training your model, now you've trained your model, it's time to make prediction. You can now predict using this linreg dot the predict function. You're not making your prediction on your test set that you reserved. And when you make prediction on the test set, it generates your predicted y. Remember, we have our real y, and now this is our predicted y. So the error you are calculating, you're going to compare the predicted y and the real y. And that's where you're going to be using your metrics, sklearn import metrics, MP, this is the root mean squared error. So by the time we finish training, our error was what? 4.45. All right, which I think it's a very good one, but it could be better. Right. So if you want to check your intercepts, you can check your intercepts, you can check your coefficients as well. Right. You can check your intercepts, you can check your coefficient. If you want to use other metrics as well, let's check other matrices. I don't know if I've done it somewhere here. Okay, I think I have it here so that I don't have to start typing and retyping. Okay, I have this one already. So let me just use this. Okay, so here we use mean squared error. Okay, I can use mean absolute error instead. So let's use mean absolute error. We have the mean absolute error, the mean squared error, and mean absolute error. All right. Okay. So when there is an error somewhere. Where is it? Okay, it's telling me mean absolute error. Okay, I've seen it. All right. Okay. There's an error somewhere. Again, print from sklearn.metrics, print line 16. There is a syntax error. If anyone is seeing it, you can please help me point my eyes to it. I've not seen the error. Okay, I think I have. Metrics.mean absolute error. All right, okay. All right, so we can see that the mean absolute error is 3, mean squared error is 19, and then the root mean squared error is 4. So you have your first model. Now it's time to evaluate the model, like show the intercepts, the coefficients. You can create a data frame. These are all the coefficients and all of that. Then you can plot your prediction against your targets. You can see that the line is there, but then it's giving you a straight line, but it's not still very, very defined. It's still very scattered. You want something that will be in a straight, like you want it to be very, very straight. You want the error to be so like this error value is still very wide, and this is still very good because this is just the baseline model. We didn't really do so much manipulations on our data set. We didn't normalize. We didn't normalize our data. We didn't do so many manipulations. We just went straight to building a model. Now, let's also check our residual. So you can also build your residual histogram. It's showing you the difference between your tests and your predicted value. So your residual histogram should be very, very well, like it should be a very normal distribution. So this is still kind of right skewed, and it can be better. So that tells you at least you built your first model. Let's try, and when you use your LinReg score, you check the score of your model. So there's a way you can also check the score of your model. It's always in maybe 0 points. It tends towards 1. If the score is perfectly 1, then it's a very, very good model. So our score is at 78. So we can improve it to get to maybe 100 or 1. All right, so that because we are multiplying by 100, that's why I'm saying 100. But if you're not multiplying by 100, we're giving you something like 0.78. Okay, so how can we further improve the performance of this feature? We can re-engineer the future, and part of re-engineering the future is we can try to here I removed LSTA and PT ratio, which is our highest correlated. That's the ones that are very, very, that are not so correlated. If you check here, PT ratio is okay. It's supposed to be annotated. I don't know why it's not showing. But if you check your PT ratio, let me reload this page, this place again. There's a problem. I have to reload it from the beginning. I don't want to reload it from the beginning, but let's just go through here. If you check your PT ratio, your PT ratio is minus, sorry, the LST is minus 0.73, which is so negative, right? And then the next one that is looking like that is the PT ratio that is very, very negative correlated. So we are removing those two features. Let's remove those two features and rebuild our model, run through. By the time we remove it, what you're just doing here is just not include them in your X test. Then all other thing remains the same. All other thing we did, like our splitting, importing our model, training, prediction, up to checking of our metrics. When we check, we can see that 4.9 is now our mean squared error as against 4.45. So it's actually improved. The error increased. So removing those two values didn't actually help the issue. It didn't help the issue because it's reduced our accuracy. Accuracy was 78. It should have been 70. It should have been better. So those two features were not the best features for us to remove. So another thing we did again was, okay, let's try to remove other features that are still lowly, that are that are not as highly correlated. So we removed cream, LSTAT, NOx, PT ratio, and task. And when we did that, we still got a higher error. It was just reducing. So in conclusion, the first model is most suitable because it had an accuracy of 78.4. So, but there are so many other things to be done to improve the accuracy score, or the error, to reduce the error. And that brings us to the feature importance of feature selection. So, but because of our time, we might not be able to touch on that. I would take out time on maybe the next class. We'll just use some, maybe 15 minutes to touch on that quickly before we go into classification algorithms. But I want you to try your hands on, replicating this, and also try your hands on that e-commerce, which will be, I'll attach you to the LMS. I'll attach it to the LMS. Try your hands on it too, so that you can try to, at least build the first model. Look at, try your hands, explore different, areas of, building your model. Try to replicate it and see what comes out of it. So I'll go through this notebook in the next class. There are different type of feature selection, the correlation matrix, and how to, what we did there was manual feature selection. So here you're going to use the feature selection. There's a module inside sklearn called feature selection. It's called the SK best function and the F regression function. So I'm going to be explaining that next class. Correlation, using your correlation statistics, or you can use your mutual information feature selection as well. Okay, so at this point, I would like to stop to take questions before we close. Do we have any questions? Do you have any questions? I'll try as much as possible to post this recording quickly so that you can get it and start trying your hands on it as well. Do you have any questions? So as you're trying that, also there is this assignment. I want you to try your hands on this assignment, this e-commerce assignment, so that you can try to attempt another data set on your own. Try to build a model on your own using this format. It does not stop here. You can keep optimizing your results by getting, you optimize your score at the end of the day. When you finish, you can optimize it to get better accuracy score or reduce your error rate. Okay. All right, so if we don't have any questions, do we have any other questions? I don't think I can see any. Okay, Bide is trying to, Bide I'll assume there are no questions. So if you have any other questions, please you can always reach out on the group. We'll be available to answer you as well. So I would upload the recording so that you can access it too. Have a wonderful evening, everybody. Bye for now.